Hello, everybody. This is Jim Corkins, and we're finishing up the very last part of rotation, and this is 5.4.1, and this is rotational momentum. So if you haven't done the reading, please do so now. And here we go. So this is rotational momentum is also referred to as angular momentum. Okay, and just like linear momentum, angular momentum is analogous to it. So where you have an M, you'll have an I, and where you'll have a V, you'll have an omega. But it all basically starts from this part right here. So let's talk about it. Suppose you had a little mass, and we'll call it mass of M. And let's say it's moving straight down right here, and it's got a velocity v. Okay? And so from our linear momentum chapter, we basically would call this we would say this point mass, it has a momentum, and that momentum would be rho, or p rather. Okay? So I'm going to actually relabel that v and call this the p vector. Okay? So it's just kind of interesting how this equation comes about, because right now you wouldn't think that a linear momentum also can also be interpreted as an angular momentum. But it can if you don't take the center of mass of the object to be, if the center of mass to be here. What if we took the center to be over here at a distance x away, at a distance r away rather? So look, we're going to take the pivot point right here versus the pivot point just following this object. Okay? And so right here, what you would say is that this mass is a distance r away, and I'm kind of drawing the right hand rule. Again, you'd point your index finger along r and point your middle finger along the momentum, and if you do that, if they're both at 90 degrees to each other, your thumb should be pointed at your own face. Okay, so this would be a positive angular momentum, right? And so what this is kind of describing right here, I'm going to use a different color. I'll use purple. I like purple. Is that if this object continued along this circle, it would be, and it was, just imagine almost like it's tied by a string to a distance r. It would continue along in this circle, and I'm not drawing a very good circle. Maybe I should erase all that and grab the circle shape from the whiteboard app that I'm using. By the way, I'm using Microsoft Whiteboard. So I'm going to insert a shape here. You know what? I don't think that's going to work. I'm going to do what's working for me, and I am just going to keep drawing that horrible, inaccurate circle. So imagine it's just swinging along this dotted line. So now this linear momentum, if it's being interpreted around this x, this pivot point, can be interpreted also as an angular momentum, right? And so how we would interpret this is that it has an angular momentum, and it's a distance r away, and it has that momentum. So in other words, that distance r times that that linear momentum is now this angular momentum. Okay? And so that's our introduction to angular momentum. But when we're talking about a solid, rigid body, okay, a solid, rigid body, and not a point mass like this. So if we're talking about a point mass, we have to interpret the momentum as such right here. We have to interpret the angular momentum as r cross p, and those are both, and those are all the little vectors. But with if it's a solid rigid body, we have to interpret the angular momentum using the moment of inertia times omega. Okay, so we're going to be applying the conservation of angular momentum to solid rigid bodies, okay, using moment of inertia and omega, okay. So as long as we're talking about a solid rigid body, we could interpret it this way. So basically the object is going to be rotating around its center of mass. And that center of mass is going to be, so we're going to be using the moment of inertia to describe that object rotating about its center of mass. And just like momentum, linear momentum, this angular momentum can have a positive or negative. If the object is rotating counterclockwise, that's going to be interpreted as a positive z-axis or a positive angular momentum. If it's rotating clockwise, that is going to be along the negative z-axis using the right-hand rule. So that's going to be considered a negative momentum, negative angular momentum. Okay. So let's do some problems. Okay. Suppose we have a person who's holding almost like an ice skater, where they're spinning about their axis, they're spinning with their arms out, and in this case, this person's holding some weights. And if you've ever watched ice skating, when you're spinning with your arms out, when you see them pull their arms in, they start to spin much faster. And then when they put their arms back out, they start to spin back to their original spin, pretty close to it, and much slower than their spin when their arms are together. Okay. So let's say this person is rotating right here. Originally, in this case, with an angular velocity of, and it looks like they're rotating clockwise, so then that's going to be a -1 radian per second. And the question is asking, when they pull their arms in, also their initial moment of inertia, we're just going to call, actually let's bring this to 2. Let's try to make it even. Actually, let's make this -4 radians per second. And their moment of inertia, let's just call this 2 kilogram meter squared. I'm just giving it a number. And so what they're saying in this problem is, suppose they're spinning, and they're spinning clockwise, and they want to know how fast they're going to, what is going to be their spin rate, omega final. That's what we need to find. When they bring their arms in. And when they bring their arms in, their final moment of inertia is going to be equal to half. Their final moment of inertia is going to be equal to half their initial. So when they bring their arms in, 1 kilogram meter per second. Again, I'm just kind of making up these numbers, but I am making sure that my negative is reflecting a clockwise spin using a right-hand rule. Okay. Well, here's a momentum bar chart for an angular momentum case. Okay. So in this case, let's say this. Let's say that they have 4 boxes of angular momentum, and this would be in the negative direction, okay, because they're spinning clockwise, which is going to be a negative omega, and so that'll then be a negative angular momentum. And so by the calculation, these 4 boxes is approximately equal to 8 kilogram meter squared per second. Okay, so that means just one box represents 2 kilogram meter per second. Okay, well, when they bring their arms in, their angular momentum initial has to be equal to the angular momentum final, as long as there's no outside impulse affecting the system, which there's not. There's no friction or any of that stuff. So the angular momentum has to be conserved. That means the initial angular momentum has to be equal to the final angular momentum. Okay? And our initial angular momentum is represented by moment of inertia initial times the initial angular velocity, and that's equal to the final moment of inertia times the final angular velocity. Well, we want to know what omega final is, so we're going to take that moment of inertia in the end and divide it onto the other side, and that's equal to our final angular momentum. Okay? Which means I'm going to give myself a little bit of room, and I'm going to zoom out. Which means that the initial moment of inertia is 2 kilogram meters squared. We're going to multiply this by the negative 4 radians per second. And now we're going to divide that by 1 kilogram meter squared. So when we multiply that all out, our units are going to cancel out, and this is going to work out to be negative 8 radians per second. Okay? What this is saying is this. So conceptually, comparing this number to our original number of negative 4 radians per second is basically saying our speed has doubled in the end. And the reason why this is since the initial angular momentum has to be equal to the final angular momentum, and this number is this number in total, I think when we compute it, would be negative 8 kilogram meter squared per second. Well, what they said this is high by 2, and this okay, let's just say let's do this. When our initial angular moment of inertia, it's got to go down by 2, right? So our initial angular momentum is twice the final angular momentum. So that means our final angular momentum is lower by 2. Well, in order to keep this total number equal to this, the final angular velocity has to go up by 2 to balance out this final angular moment of inertia to be equal to the total. So since this has got to go down by 2, this has got to go up by 2, so it's equal. So they maintain being equal to 8, right? So that's the reason. That's conceptually the reason why this has to go up to balance out that lowering moment of inertia. So I hope that kind of helps a little bit put this into perspective. And this is also, again, I'm kind of reminding you that we are going to be using momentum bar charts to solve these problems. Okay? let's move on to an actual problem that is a little bit more complex. Because when we're talking about momentum, we also talked about elastic collisions and inelastic collisions. Well, this is the case where the inelastic, this is an inelastic collision case. And this actually has, again, this has two parts to it. The first part is describing here where you've got a mass falling onto a disk that is spinning counterclockwise. So it's going to have a positive angular momentum. But since this mass is falling straight down and it's not spinning reference, it has no angular momentum relative to itself, it's only got linear momentum, it essentially has no angular momentum, right? And then it's going to hit and stick to this disk. So let's put some numbers in here, okay, to actually give this more of a concrete problem. This problem is described in abstract values, but I like to make things more concrete. So I'm going to say this, the disk, let's say the disk's moment of inertia, that equation is going to be 1/2 mr squared. And let's just call that mass 2 kilograms, and let's say it has a radius of 2 meters, right? So if the mass of the disk is 2 kilograms, and I like using capital R, so I'm going to erase this. And let's say the disk has a mass of 2 kilograms. And it has a radius, we'll call it a radius of 2 meters. Why not? So the moment of inertia of this disk is going to be 1/2 mr squared. So that's going to be 2 meters times 1/2, so that's just 1 meter. And then 2 kilograms, 2 kilograms times 1/2, that's going to be 1 kilogram times 2 meters squared, so that's going to be 4. Overall, this is going to be 4 kilogram meters squared. Let's say the block, the mass of the block is going to be 1 kilogram. Let's just say it weighs about half the mass of the disk. Okay? So let's do this first part where you got a block that's falling straight down. It's not rotating or spinning, so it has no angular momentum. And it's going to stick to the outer edge of this wheel. And when that happens, and this wheel is going to be spinning, and let's say this wheel is spinning at the initial angular momentum, angular velocity is, we'll call it, let's call it 4 radians per second. And that's going to be a positive because it's rotating counterclockwise, right? So the disk's moment of inertia is going to be 4 kilograms, and the angular momentum of this disk looks like it's going to be about 16. So let's give this 4 blocks of positive angular momentum right here. And the block, so this is the block, this is the disk, this is the disk plus the block, okay? And so I should probably also mark these other things too. The disk is number 1 and the block is number 2. And the disk is number 1 and the block is number 2. So anyways, you have the disk that's spinning counterclockwise, and then you have the block that is essentially, it has no angular momentum. So this is 0. And so when the block hits the disk and sticks to it, since that angular momentum is going to be conserved, the initial angular momentum of the disk is going to be equal to the final angular momentum of the block and the disk. We're going to call this a perfect inelastic impact, so there's no energy loss. There's probably going to be energy loss, but there's no loss of momentum due to friction or any of that stuff. Okay, so when we solve this problem using the values that we have up top, right here, we're going to start off by saying the initial angular momentum is equal to the final angular momentum. The initial angular momentum is the moment of inertia of the disk plus the initial angular velocity of the disk. That's going to be equal to the moment of inertia of the disk, but it also has the block sticking at the end now. And now the block will be spinning. And they'll both be spinning counterclockwise, probably. 99% sure. So, again, as we stated up here, the disk has a moment of inertia of 1/2 mr squared. And since its mass is 2 kilograms and its radius is 2 meters, that's going to be a total of 4 kilogram meters squared. And that's going to be multiplied by the positive 4 radians per second that we made up just for this problem. Well, in the end, that disk's moment of inertia hasn't changed. Okay, that's still 4 kilogram meter squared. But now we have to add to that the block's moment of inertia, which is kind of like a ball on a string. Okay, it's going to have the same effect, which that's going to be 1 kilogram times, and since it fell and stuck to the edge, 2 meters, that's going to be meter mr squared is that equation. So we're going to be adding this total moment of inertia together and multiplying it by this. Okay. So we have to remember that this is 2 meters that we have to still square. So that's going to be 4 meters squared times 1 kilogram, right? So this on this side is going to work out to be 16 kilogram meters squared per second. And this is going to be 4 kilograms plus 4 kilogram meters squared. So this is going to work out to be a total of 8 kilogram meters squared times omega final. Okay? So when you bring this onto the other side, you get 2 radians per second as omega final. So it's going to slow down. In this case, it's since the moment of inertia from the values I picked is going up by essentially doubling, then that means the angular momentum is going to go down by 2, right? So again, very similar to this problem, since angular momentum is being conserved, if this side has to be equal to this side, so if this, in our case, the moment of inertia is going up here, in our case, this is increasing, so this has to decrease, right? It's increasing due to that inelastic impact, right? Okay, well, that's the first part of the problem, okay? The second part of the problem, in fact, I'm going to take this area right here I'm going to move this all over here because this is going to reference this bar chart. I need room to do my other bar chart. So now, given that in this case, it's now spinning with this moment of inertia, they're saying this, now this block slides or grows legs in some way and slides to the center in this final case, such that it's now sitting at the exact center. Okay? And before we continue on, so that again, when it slides to that exact center, it's not going to have, that block is not going to have any angular momentum. Okay? But before we continue on, I did make a little mistake earlier. I should have referred to this middle case as not L final, omega final, and such. It should be L middle, omega middle, all the way here, because we were terming the spinning in this case, right in this case, which is the middle case. Since we're going to be needing the F for this to be the final, I want to make sure that that is referenced as the middle angular momentum. But anyways, let's continue on with this. So here we have the disk and the block spinning. Okay, and we already know that total moment of inertia right there. So we have the angular momentum of this, sort of. And this is going to be equal to the angular momentum final. That angular momentum right here is the same as in this case. That's going to be the moment of inertia of the disk plus the moment of inertia of the block times omega middle, right? And we know this number to be 2 squared times 1 kilogram. So this is 4 and this is 4. So that's a total of 8 kilogram meters squared times 2 radians per second. So that's going to be a total of 16 kilogram meters squared per second. Okay. So we already know that left side. The right side is going to be an interesting case because we can't just plug in the moment of inertia of the disk because now the mass of the disk has actually increased. Okay? So it's not as clear-cut. This is going to be a concern here. We're going to actually have to rewrite this to include the mass of the block. And I'll tell you what I'm talking about in a second. So if it was just the mass of the disk spinning, you would have 1/2 the mass of the disk times the size of that disk squared. But since the block is now sitting on that disk, this moment of inertia is going to be equal to the mass of the disk plus the block's mass times omega final. Okay, you have to include both of those there. So this right, not times omega final, times r squared times omega final. So this right here is going to be equal to, so this is now the new moment of inertia for the disk. That's the mass of the disk plus the block's mass times the size of that disk, which I think we called is 2 meters radius. So this is going to be 2 meters radius squared times omega final. So this over here is going to be, that's going to be 3. This 2 is going to get canceled out. So this is going to be a total of 6 kilogram meter squared. Just to be sure, this is 3 times 2 times 2. So that's 18 And one of those 2's gets canceled out, so this is basically 3 times 2. Cool, omega final. And this is 16 kilogram meters squared per second on this side. So now, to solve for omega final, this 16 is going to be divided by 6. So I'm going to pull out my calculator. 16 divided by 6 equals 2.667. So 2.667 radians per second. So here's what this means. This basically means it starts out spinning at 4 radians per second. When the block lands in the middle on this and sticks to it, it now slows down to 2 radians per second. But since the block has added its mass to this total object's mass, the disk and the block, when the block moves to the center, its angular momentum disappears, but since its mass is still there, it's contributing to that mass of that disk, and now it's not able to get back up to its original speed. It's going to be faster than this speed here, but it's not going to be quite as fast as its original speed. So that's this problem from beginning to end. In the beginning, they were asking, compare the omega here to the omega here to the omega here. And what happens is it's always spinning the fastest in the beginning, but then it spins slower here in the middle. But since this block goes to the center, its angular momentum disappears, but it can't speed back up to its original speed because this mass is added to the total object. So now it's not able to get back up to its original speed. All right, that's the problem from beginning to end. Okay. Another classic problem that we have to do, that we typically have to do, is suppose you have, and this is less complicated, you have one disk spinning, and again, let's call this disk. Let's actually change it up. Let's call this disk that's spinning. Let's call it, again, spinning at positive 4 radians per second. And that's the initial angular velocity. That's the initial angular velocity. We want to know the final angular velocity. So this disk has an initial angular velocity of 4 radians per second. And let's say that disk, that big disk, the big one, so that we'll call this big disk right here. So this is big disk, and this will be small disk. So that big disk, we'll say since it's bigger, it's got twice the mass and twice the size. Okay, it's not quite the size. Let's say, well, I'm putting numbers in. Let's say that big disk has twice the mass, so let's call that 2 kilograms, and it's got twice the size, so that's going to be 2 meters that we're going to square. So this is going to be 4 kilogram meters squared. Okay. And so this big disk is spinning, and the smaller disk and we'll call this small disk with an S. So this is big plus small. Let's say that small disk has half the mass and half the radius. Okay. So this is going to be 1/2 times 1 times 1. So this is going to be 1/2 kilogram meter squared. Okay, and this is the small disk. So this big disk is spinning, the small disk is not spinning, but it's going to fall and stick to the big disk. And in the end, they want to know what is the final angular momentum, final angular velocity in this case happens. So given these values, why don't you pause the video and try it out. So please pause it now. Okay, so in the beginning, the big disk is spinning, and we'll call that 4 blocks. Okay. Actually, let's call it 3 blocks. Actually, let's call it 2 blocks. Sorry. And the small disk is not spinning, but it is going to fall down. And then, in the end, the small disk, the big disk is spinning. Again, it's still spinning, but now the small disk is now stuck to it. So again, we have the same situation where there's no outside impulses. We have the initial angular momentum equal to the final angular momentum, and in this case, the moment of inertia for the big disk times the big disk's initial angular velocity, which is going to be 4 radians per second and 4 kilogram meter per second meter squared. So this is going to be, we determined it before, 4 kilogram meter squared times 4 radians per second. Okay. Well, in the end, the big disk's moment of inertia is now being added to the small disk's moment of inertia, and that's their final angular velocity. Lost a little bit of room here. So this is going to be 4 kilogram meter squared times 4 radians per second. That's going to be equal 16 kilogram meter squared per second on the left-hand side. On the right-hand side, this is 4 kilogram meter squared plus a half kilogram meter squared. It's just the way it worked out, omega final. So this is going to be 4.5 kilogram meter squared times omega final. So it looks like it's going to be smaller by just a little bit different from a half. So 16 divided by 4.5 equals 3.56. So omega final here is going to be equal to 3.56 radians per second. So it's going to slow down by just over a half. Seeing that its mass is only increasing in the end, its moment of inertia is only increasing by a half due to that smaller disk. It's not going to the velocity, the angular velocity in the end is only going to change by just a little bit. It started out at 4 radians per second. Now it's only at 3.56 radians per second. So I also wanted to introduce this problem to you because it doesn't always work out to be whole numbers, and it doesn't always work out to be perfectly proportional, right? One goes up by 2, the other one goes down by 2. It doesn't always work out like that. Sometimes you have a moment of inertia that's not equal to a whole number, and it's like a fraction, and that's how it can change things. Okay, this is how to handle this type of problem. Okay, So let's talk about this next one. This is a larger type of problem. It talks about how when you compare a spinning hoop and a spinning cylinder, both have the same mass and radius and a same applied torque. And they want to know in the end, they want to answer all of these questions in the end. So this is almost like a review of everything that we've done. Okay, so here's how to handle this type of problem. So they want to know which one has a bigger moment of inertia, and obviously those moment of inertias are here. This hoop, if it has the same mass and radius, has a moment of inertia of mr squared. Okay? And the disc has a moment of inertia. So this is the hoop, and this is the disc. Has a moment of inertia of 1/2 mr squared. Now, moment of inertia of the hoop is going to be twice as high as the disc's moment of inertia. Next part, they're asking about angular acceleration. Well, torque over moment of inertia is going to be equal to the angular acceleration. So this guy's angular acceleration is going to be equal to the same torque. They're both given the same torque, but this is mr squared. I like capital R's. Why do I keep using lowercase r's? I'm just going to make those capital R's. Why don't I listen to myself? Anyways, for the disc, its torque divided by its moment of inertia is equal to its alpha as well. So this is the hoop and this is the disc. So it is going to be 1 over 1/2 mr squared, which is going to work out to be basically this is going to be 1 times torque over mr squared, and this angular acceleration is going to be 2 times the torque over mr squared. So that means if we call torque over mr squared just equal to alpha, let's just call that alpha, and this is alpha, that means the hoops, this means what altogether this means is the hoops angular acceleration is going to be 1 times an angular acceleration, but the disk's angular acceleration is going to be twice of that of the hoop. Angular acceleration of the disk is going to be twice that of the hoop. It's going to be twice the angular acceleration. Okay? And this is all with proportions. But again, I'm trying to assign some numbers to work it out. The next question is asking about angular kinetic energy. Well, in order to answer that question, we kind of have to do this middle step. If we want to know the kinetic energy of the two objects, kinetic energy is going to be equal to 1/2 I omega squared. We have the I part, we don't have the omega squared part, but we can get omega squared. So what we're going to do is relate alpha to omega, okay? And I don't know if you remember, but omega final minus omega equals omega initial plus alpha times t, okay? So omega final minus omega initial is equal to alpha times t. So delta omega is going to be delta omega, which is a total change in omega. That's going to be equal to alpha times t. So what we could say is this, and given that they're the same period of time, if alpha goes up, omega is going to go up. So to determine the omega here, omega for the hoop, well, if it's got 1 times the alpha, that means it's going to be equal to 1 omega, right? So in other words, what we could say is this, is that if omega of the hoop has 1 alpha, then the omega of the hoop is going to basically just be, is just going to be 1 times, since alpha is going up by 1, the hoop is going to be just 1. So that's going to be 1 omega. We're going to kind of use omega as the units. But with the disk, the omega of the disk, that has 2 alphas. And so the omega of the disk, since alpha is going up by 2 here, omega is going to go up by 2. So this is going to be like 2 omega. All right. And so to find out the kinetic energy part, what we're going to use is we're just going to use the equation right here for kinetic energy. I'm going to bring this over here, and we're going to kind of calculate those right here. Might need some more room. Well, for the kinetic energy of the disk, for the hoop, I mean, that's going to be equal to 1/2 mr squared times omega squared. Pretty easy. For the kinetic energy of the disk, well, that's going to be equal to, for the disk, well, this is 1/2, but its moment of inertia is 1/2 mr squared, right? The moment of inertia of the hoop is just mr squared. And also, since the disk is now spinning at twice the omega of the hoop, we're going to have to square that. So this is going to work out to be 1/2 times 1/2 times, so this is 2 squared times omega squared times 1/2 times 1/2. So this is going to work out to be mr squared omega squared. So the disk is going to have twice the kinetic energy of the hoop. Okay? And so the reason why it has twice the kinetic energy, even though it has half the moment of inertia, is because this omega is being squared. And since it's got twice the omega, but it's being squared, it's going to end up going to be having twice the kinetic energy. To answer the last part of the problem, is they're asking about angular momentum. Okay, so we're going to need this angular velocity stuff. So what I'm going to do is I'm going to grab this. Oops. I need to grab the entire thing. And I'm going to move it up. Okay, and I got to grab this guy and move it up here. Okay, so let's try this again. Move it up. Because the reason why I'm moving it up is that this kinetic energy, this angular velocity stuff helps to solve 2 problems. It helps to solve the kinetic energy stuff, okay, but it also helps to solve the angular momentum stuff as well. So now, so in other words, I guess what I'm saying is this angular velocity stuff helps solve the kinetic energy stuff. But the last question is, how does all of this, what we've just passed on, all the way up to angular velocity, affect kinetic energy, but also angular momentum? Well, we're going to use this angular velocity stuff to help us with the angular momentum. So the angular momentum of the hoop is its moment of inertia, which is mr squared, times its angular velocity, which is just omega. The moment of inertia of the disk is going to have 1/2 mr squared, but it has a 2 omega. So that's going to work out to be mr squared times omega. So even though their kinetic energies are different, their angular momentums will be the same. And that is because the moment of inertia for the disk is half, but it's spinning twice as fast. That kind of balances out with the hoop's angular momentum of 1. So I hope this helps kind of how you could just really quickly, using your concepts, analyze, starting out with a problem like this where two objects have the same radius, the same mass, the same torque, and are spinning over the same period of time, and how you can start with a moment of inertia, and then using torque, solve for the angular acceleration, and then using angular acceleration to eventually get understandings of kinetic energy and momentum using angular velocity. Okay, this very last part that we're going to do is kind of an optional part. Typically, you're not going to be asked this type of problem in Physics 112 because it's a very complicated problem. It looks very simple. What you have is you have a disk. You have a disk and a hoop, so almost like the last problem, but they're going to have an elastic impact. So you have the disk and the hoop. They both have the same mass and same radius, mass of 2 kilograms and a radius of 0.5 meters. The disk is moving with a linear velocity of 6 meters per second, and it's rolling towards, and it's going to hit a stationary hoop. When they impact each other, the question is asking what is going to be the final velocity of the disk, and I'll actually use this is the disk, and what is the final velocity of the hoop. Okay. So what we're going to have to do is we're going to have to analyze this problem both with kinetic energy, but also with linear momentum. Okay, so let's do a couple things. I don't know why that's here. So let's take a look at this. Let's just use angular momentum really quick. Okay, so this is the mass of the disk times its velocity. So I'm going to use linear momentum. Okay, so the mass of the disk, I think we said is 2 kilograms. So the mass of this disk is 2 kilograms. And the mass of this is also 2 kilograms. 2 kilograms and 2 kilograms. So the disk's momentum is going to be, linear momentum is 2 kilograms times a positive 6 meters per second. We're going to add that to the momentum of the hoop, which is going to be 0 kilogram meters per second. And that's going to be equal to the disk's final momentum, which is 2 kilograms times VD, plus 2 kilograms times the velocity of the hoop. So the final velocity of the disk, final velocity of the hoop. In this problem, the 2 kilograms are going to cancel out. Again, this is just 0, so it's not affected. So what we could say is the initial velocity of the disk is going to be equal to the final velocity of the hoop plus the disk. Okay, that's pretty easy to do. I could use energy bar charts for this, but I'm not, because it's kind of a larger problem. But what we want to do is calculate all the kinetic energies of the disk, through the disk and the hoop all together, all at once, across the entire impact. So what we're going to say is this. In the beginning, we're just going to go right to the equations. In the beginning, the disk has a initial linear kinetic energy, and it's also got initial rotational kinetic energy. Okay. In the end, the disk has a final linear kinetic energy, and this is the disk, this is the disk, this is the disk, and it's going to have a final rotational kinetic energy for the disk. But this hoop is also going to be moving, so it's going to have a linear kinetic energy in the end, plus a rotational kinetic energy in the end. This should be F final. So it's kind of a big equation, okay? But it kind of works out. I try to keep it simple. So the linear kinetic energy for the disk is going to be 1/2 the mass times the velocity squared, which is 6 meters per second squared, plus the disk has 1/2, and its moment of inertia of the disk times its rolling speed, its omega, its initial omega squared. That's going to be equal to 1/2 the disks. They all have the same mass, times its final speed squared, plus 1/2 the disk's moment of inertia times its final velocity squared, plus 1/2 the hoop's linear velocity squared, 1/2 the hoop's kinetic energy, plus 1/2 the hoop's rotational kinetic energy. Whew! We're going to have to plug in some numbers here. We're going to need this linear energy problem to actually solve for this. So I'm going to try to copy this as quickly as I can on this side. But now we have to start putting in our equations. The disk, the moment of inertia for this disk is 1/2 mr squared. And they have the same mass and same radius. The angular velocity, again, just to remind you, is equal to the linear velocity divided by the radius. So this angular velocity of the disk is going to be equal to 6 meters per second squared divided by the radius squared. Okay. That's going to be equal to 1/2 the mass times the linear velocity of the disk after the impact plus the 1/2, and I'm going to need more room, plus the kinetic energy of the disk after the impact. And so this is going to be 1/2 mr squared. So that the disk's moment of inertia is the same, but after the impact, the velocity of the disk is going to be squared over the radius squared. So after the impact, it's got this omega, which again is v over r, so it'll be vd over r squared, plus, this is getting big, 1/2 m mass, the linear kinetic energy of the hoop squared, plus 1/2 the moment of inertia for the disk, for the hoop, which is just mr squared, times its velocity of the hoop. I put in d there. Should make that an h. I apologize. Squared over the radius squared. Oh my goodness, this looks horrendous. But it's kind of neat because a lot of things are going to cancel out. Okay. R squared here is going to cancel out with this r squared. The r squared here is going to cancel out with this r squared. The r squared here is going to cancel out with this r squared. Okay. So just keep following along. Since they all have the same mass, this mass is this mass, which is this mass, and this mass, this mass, and this mass. So the masses will all be the same. But since they all have a 1/2 in the front, that 1/2 and this 1/2 and this 1/2 and this 1/2 will cancel. It'll cancel out these 1/2s all across. And I should have used a different color to track that. So I'll use green to show that the 1/2s are canceling. Since you got a 1/2 here and a 1/2 here, they have a common 1/2. You could multiply by 2. Essentially, I'm multiplying the entire equation by 2, which will take out this 1/2 and this 1/2. It'll leave this one here, but this 1/2 will be canceled out, and this 1/2 will be canceled out, but it'll leave one of the 1/2s here. But this 1/2 and this 1/2 will be canceled out. So all of this is going to look like, grab my little notation here. So 6 meters per second squared is going to be 36 meters per second squared, plus 6 meters per second squared times a half. This times a half. So that's going to be 18 meters squared per second squared. That means this total left-hand side is going to end up being 54 meters squared per second squared. On the right-hand side, we're going to have VD squared plus 1/2 VD squared. All right, so that took care of this. Plus VH squared plus VH squared. So this is going to be VD squared. So this is going to be 3/2 VD squared when you put these two together, plus 2 VH squared. All right. What I think I'm going to do is I'm going to take this equation up here, and I think it'll be easiest if I solve this equation right here and solve it for VH and then substitute it into here. That way we could get rid of the VH variable. Here's what I'm talking about. So 6 meters per second equals VD plus VH. So I'm going to take that VD and subtract it onto the other side. V sub H. Okay. So we have two equations and two unknowns. We need to eliminate one of the unknowns. So we're going to take the simple equation. We're going to want to eliminate VH. So we solve it for VH. That way when we plug it into here, we get something that's that way we'll get all of this in terms of just VD. But before we do it, let's simplify this a little bit. Let's divide everything by 2, right? I want this to be as simple as we could get before we plug it into here. So if we divide everything by 2, 54 divided by 2 is going to be 27 meters squared per second squared. That's going to be equal to 3/4 VD squared plus VH squared. Okay. Let me make that look a little bit cleaner. VH squared. Okay. So when we go ahead and we're going to eventually plug that in, and I think before we do that, I should square this VH. So I got to square everything here. Let's square VH. That means we need to square this. That means we're going to have 6 meters per second minus VD times 6 meters per second minus VD. Okay, and this will be VH squared. So 6 meters per second times 6 meters per second is 36 meters per second. Then we're going to have 6 meters per second times a negative VD plus 6 meters per second times a negative VD. That's going to be negative 12 meters per second times VD. And this should be squareds here. And then finally, negative VD times negative VD is positive VD squared. And that's going to be equal to VH squared. So now we could take this whole thing right here and substitute it in for VH. And when we do that, we're going to get something that looks like this. So I'm going to need a little room. I'm going to move my cursor over here. I'm going to copy everything from up here. But now I'm going to add on this. 36 meters squared per second squared minus 12 meters per second VD plus VD squared. Okay. Well, we're going to have to start putting some things together. What I'm going to do is subtract the 27 meters per second onto the other side. So I'm going to bring the numbers to the front. Minus 27 meters squared per second squared. Okay. And next will come the VDs. This will be plus 3/4 VD squared plus this VD squared. And then finally the negative 12 meters per second VD. Okay. So So I need a little bit of room. 36 minus 27. So that's going to be 9 meters squared per second squared, plus 3/4 plus 1 is going to be 7/4 VD squared minus 12 meters per second VD. Okay. All right. Let's see what we have now. I'm going to put this into a presentable form. This is going to be 0. I'm going to bring this to the front. 7 divided by 4 VD squared minus 12 meters per second VD plus 9 meters squared per second squared. Okay. So we're going to have to use we're going to have to use a quadratic equation to solve for this. So this 7/4 is going to be our A. Actually, so the 7/4 is going to be our A coefficient. -12 is going to be our B coefficient. And this last one is going to be our C coefficient. So when we use the quadratic equation calculation on this, when we use our quadratic equation calculation on this, what we get is that VD could be one of two things. It could be 6 meters per second, or it could be 0.85 meters per second. It's going to be one of those two things. And I'm pretty sure that when the disc rolls downhill, well, the disc rolls and it hits the hoop, that it's not going to keep rolling at 6 meters per second. So that leaves this as the only logical answer to this problem. So we're just going to go ahead and say that VD is not going to be 6 meters per second. In fact, this is going to be VD. Okay? So this is going to be the velocity after the impact, and it's going to be positive. So that is 0.85 is going to be the speed of the disc after impact. Now to find the speed of the hoop after the impact, what we're going to do is we're going to use the equation that we created right here, and I'm going to copy that down here. Okay. That's going to be 6 meters per second, and that came from our linear momentum equation. And this is the hoop. So if we plug in our realistic value for the speed of the disc after the impact, this is going to be 6 meters per second minus 0.85 meters per second. And that's going to be the velocity of the hoop after the impact. Okay? So let's go ahead and pull out a calculator. Well, actually I don't really need to do that. So this is going to be 5.15 meters per second after the impact. And that's going to be the velocity of the hoop. Okay? So that hoop is going to, that disc is going to roll initially at 6 meters per second. It's going to hit that stationary hoop. and then that disk is going to keep rolling forward at 0.85 meters per second, and then the hoop is going to take off moving forward at 5.15 meters per second. And that is the entire problem here. And that ends our last part of 5.0 of rotational motion. I hope you enjoyed it. Thank you very much.